Okay, so for now we have our last talk. This talk will be by Professor Jahna Otterbacher, and she will talk us about bias in data and algorithmic systems, problem, solution, and stakeholders.
Thank you, Kalia, for the introduction. Welcome back, everybody, from the break. It's a pleasure to see you again on day 2 of our winter school. And I'm very happy to have the chance to share with you some of the research coming out of our project, and also some that's being undertaken on the ground here in Cyprus. So what I plan to do in this talk is, first of all, share with you a conceptual framework that we developed in order to understand the growing and very complex body of literature that's being published concerning bias in data and algorithmic systems. And then I'll switch gears and give you 2 examples of empirical studies which were carried out by our research team here in Cyprus. Now, just quickly, you'll notice that a 3rd logo has appeared on my title screen there, and that is Science Center of Excellence. It was formerly known as RISE, if some of you know it by that name. This is a research center which is also located here in Nicosia, Cyprus, and at which I spend part of my time, approximately 1 day a week. So that's there just because the 2 empirical studies that I'll be telling you about are joint collaborations with our colleagues there. So let's get started. Of course, everyone is talking about social bias and algorithmic systems and big data analytics, and we saw a lot of examples with Michael and Jahna yesterday, as well as in decision support systems in Svika's talk earlier today. But I just like to give a couple of quick examples to get back into the the spirit of things here. So as we all know, it's becoming increasingly urgent that researchers and practitioners take measures to mitigate the negative impacts of algorithmic bias in the social world and in people's lives. These are some news headlines that probably caught your attention. So on the left-hand side, we have the case of the Microsoft Tay chatbot. So this was put up at Twitter and interacted with the public in order to showcase the company's natural language processing algorithms. But they had a little problem with it, and they had to take it down within 24 hours. Anyone want to venture to say maybe what was a strategic, I mean, basically what happened, as you can see on the headline, is that the bot learned the worst of our behaviors as people, right? Within 24 hours, it learned to be a sexist, racist jerk, basically. Anyone want to take a wild guess in the chat there, just to make sure that you're there? Maybe what's the strategic mistake here? Okay, well, we can discuss it later as well. Hello, Berta. I would venture to say that giving the bot a, repeat the question, sure, happy to. I was just gonna say that this Twitter bot within 24 hours had learned to be, had learned the worst of us, right, by interacting with the public. And I was wondering if anyone wants to weigh in as to maybe what was the strategic mistake of Microsoft with this bot? Not monitoring what the bot learns. They didn't use any filtering techniques, no boundaries and filtering. Yeah, this is all true. The majority is what they got. Yeah, the worst of us. I was going to venture to say that creating this persona of a teen girl was maybe a bit risky as well. People did not behave well towards this bot. In any case, enough about that. On the right side of the slide, we have the case of IBM's facial recognition technology. So a lot of research, of course, is coming out in the past couple of years on computer vision, and there's increasing evidence, of course, that computer vision applications such as facial recognition have, they don't treat everyone in the same way, right? And that there tend to be increased error rates when they are analyzing images of women and of people of color. And there's increasing pressure for companies to be very careful about how they use this technology. Now, you notice the particular headline there is one from this past June, and IBM came out and announced that given all these problems and the inherent social biases in these algorithms, that it's going to stop offering its facial recognition software for applications involving quote unquote mass surveillance or racial profiling. So we can ask Casey about that tomorrow. Okay, just the third case, which is a bit older, but I like to use this one. We have the case of the Gorilla Photos app, the Gorilla incident. So this is an incident that came to light back in 2015, and you can see the man in the photos there. He, of course, had uploaded this photo of himself with his friend to the photo app, which of course automatically assigns, it uses an image tagging algorithm to automatically provide descriptive tags on images, and you can see what happened. Obviously, this went viral. He posted it on Twitter. Google promised, of course, Google apologized. They promised to roll out a solution. Well, we got the solution in 2018. They announced their fix, and it was simply to remove the offending word, gorillas, and other related words from the database of the image tagging algorithm. So there are, of course, many different examples of algorithmic bias that we can discuss. But the reason that I like to start out my talks with these is that, you know, what we essentially have here are major tech companies, the experts, right, coming out and essentially admitting that they don't know how to solve these very complex technical issues behind bias, right? And I think it speaks volumes concerning the problem that we're dealing with here, especially if we are attempting to realize this vision that we have here in Europe for ethical and trustworthy AI. So I already told you a little bit about SciCat as well as the SciCat project yesterday. You might remember that the project launched in October of 2018, and like many collaborative projects, we kicked things off by performing a survey of the literature with the goal of understanding the state of the art on mitigating algorithmic bias in information systems. Okay, so those of you who've been working in this area or studying in this area for a while, you might say, well, okay, Jahna, there are already a lot of surveys. Do we really need another one? So you'll know that several comprehensive survey papers have been published over the past couple of years. Some of them are shown here on the slide. What we discovered, though, is that most of these surveys are either very specific or very broad in nature. So for instance, some of them focus on very particular problems of data bias. Some of them focus on solutions for explaining black boxes, as you see there. Some of them are very introductory. So in contrast, what we wanted to do is to try to make sense of this whole landscape of literature, because it is a little bit intimidating, I think, for people first starting out, through what we're calling a fisheye view approach. Now, some of you who are photographers might know very well what a fisheye view is, and this is an example of a fisheye camera lens, which is, of course, a circular, very wide angle lens, which hones in on the objects nearby while shrinking those that are in the distance, that are in the background. So this is, of course, a visual distortion. It's not what reality looks like, but it provides an advantage of highlighting the local details while still preserving the local context. You can still understand where you are, right? Undoubtedly, most of you will be familiar with this. You will have seen this before. In 1986, in a 1986 ACM Chi paper, cognitive psychologist George Furness of the University of Michigan developed a concept for generalized fisheye views in visualizing information spaces. And he actually found in his research that fisheye views are naturally occurring. So when representing large information structures in their head, people tend to preserve lots of detail about objects that are either quote unquote close to them, important in their lives or that are of major importance a priori. So Furness also makes reference to this famous 1976 cover of The New Yorker by Saul Steinberg, which portrays the view of the world from 9th Avenue. Okay, so why do we need such a fisheye view for understanding the landscape of research on this topic? Well, the research has become very complex in recent years because, as we all know, the attention that this topic is receiving has really exploded very recently. So these are the first page results from my Google Scholar search on algorithmic bias from sitting here in my office. And I wanted to show you kind of the diversity of the literature here. So in red, I have indicated the research community to which each article is directed. And in blue, I've tried to indicate the stakeholders which are mentioned in each article. So even from this super quick analysis, we can see that the body of literature on algorithmic bias is very diverse, both in terms of its focus and also in terms of the audience. So Michael told us a little bit yesterday about the COMPAS case study in his presentation. This is a study which arguably helped to stimulate both public debate as well as research in the area of mitigating algorithmic bias. So just to repeat, in case some of you don't know, COMPAS is a proprietary decision support system which until recently was used quite extensively in the United States in the criminal justice system to predict a defendant's likelihood of reoffending. In other words, it aided judges' decisions in sentencing. But in 2016, a team of data journalists published an article in ProPublica exposing the system as suffering from racial bias and that its error rates for Black defendants were much higher than for those of their white counterparts. I'm making it even more simple here. They had quite a lot of findings that came out of that, but that was the gist of it. So the COMPAS case study clearly illustrates the fact that multiple stakeholders and multiple processes are involved in addressing algorithmic bias. So since the ProPublica piece was published in 2016, there have been literally hundreds of research articles published about this particular system. And here I've illustrated for you just a few of the different research questions and research approaches that we can find in the literature. So the ProPublica data journalists, of course, asked whether or not COMPAS system reflects group fairness. So whether or not it treats different racial groups of defendants in a similar manner. And of course, they found evidence that it indeed does not. Meanwhile, computer scientist John Kleinberg and colleagues pointed out that there are multiple notions of fairness that are important in the context of a system such as COMPAS. They demonstrated that it is typically not feasible to respect multiple definitions simultaneously. So in other words, there's going to always be a trade-off between which type of fairness you're going to respect. Other researchers have emphasized the role of transparency, both of the data and of the algorithm, in ensuring fairness in the system. And then finally, interestingly enough, some have highlighted the role of the user in mitigating bias. So Ridgway in particular noted that the user must have sufficient statistics literacy as well as practical knowledge of the justice system in order to interpret and apply the COMPAS output appropriately and effectively. Okay, finally, this will be also very familiar to most of you. So we can also find motivation for developing this fisheye view of the field from the ACM statement on algorithmic transparency and accountability. So as most of you probably know, this was a statement that was published in 2017, and it includes 7 guiding principles for researchers and practitioners. Apparently, it was one of the rare times when the U.S. Public Policy Council agreed with the Europe Council. In having a look at these 7 principles, I'm counting at least 7 different stakeholders who are mentioned in them, from the owners of algorithmic processes or systems to those involved in any way in their development, to regulators, and of course to the users themselves. So in summary, what we can conclude from all of this is that comprehensive solutions for addressing algorithmic bias are not to be found within a single research community or from one individual perspective alone. So the primary intent of our survey is to describe the broad landscape of research concerning the mitigation of bias in algorithmic processes and systems. So in particular, we wanted to examine the problems and solutions in the literature that are being addressed and proposed across different research communities. And we wanted to better understand how the problems map onto the solutions and also which stakeholders are involved in all of this. Okay, so our first contribution, and by the way, this literature survey, it's not yet been published, it's still under review, but we do have a deliverable from our project, which is sort of a short summary of all of this published at our website if you're interested. So our first contribution is a repository of articles on mitigating algorithmic bias, as well as a methodology of how in the world we can go about analyzing this very diverse set of articles. So this is kind of a live deliverable or a live project which we're hoping to update over time. So for our initial iteration, we focused on the research communities of the SciCat project partners, and we used publication venues as a proxy for research communities, which of course are notoriously difficult to define precisely. So the 4 domains of the research that we focused on are machine learning, information retrieval, recommender systems, and human-computer interaction, HCI. And we also left an other category for some of the more emerging research communities. What we did was to do a systematic literature review. We searched on the keywords that you see there on the slide. And we looked at the literature published over a decade from 2009 to 2019. An important caveat is that our repository of articles contains only those that describe a particular system or algorithmic process. So we did not focus on more abstract or philosophical works. So we do have a link there to our Zotero repository, which is publicly available, which you can feel free to use if it's helpful to you. Each article in that repository has been analyzed and labeled with respect to 3 attributes, which I will tell you about right now. So the first attribute that we considered was the problematic component or components. Oftentimes it is more than one. Of the system being examined as described by the authors. So to do this, we use the generic machine learning architecture that you see on the slide. So you can see there all of the usual suspects: training data, an algorithmic model, input, output, the user. But then there are 2 others that you don't always find in this pipeline. So you'll see that we have fairness constraints. Svika alluded to those in his presentation earlier. So fairness constraints may be introduced within a system such that a particular notion of fairness is prioritized in the algorithmic model. So these are constraints which would obviously have to be imposed by the developers. Likewise, the influence of third parties can sometimes also be a source of bias. So one example might be in a recommender system where there's a large population of users, and the preference of other system operators, users, might affect the system's behavior, in turn affecting the results that a particular user receives. Another typical example is the regulation of search engines, which often have to be modified or constrained to comply with local laws. So as an example, the Google search engine, which needs to be modified in order to comply with GDPR or the right to be forgotten here in the European Union. Okay, moving on to the second attribute that we labeled in each article. So we labeled the attribute or attributes, again, it can be more than one, affected by the bias. And you'll see that some of these are a bit overlapping. It's important for me to tell you here that we used the terminology we recorded the terminology that was used by the authors themselves. So what you see here on the slide is a frequency analysis of the effective attributes described in the articles, which are also broken out by the 4 research domains, actually 5. We have other in there as well. So basically, we found that the attributes which are affected by bias fall into 2 broad categories. So in particular, they concern either people, such as their sensitive or demographic characteristics, or they concern knowledge or information. So with respect to information as an affected attribute, because you first might say, okay, how can that be affected by bias? We observe that many articles from the domains of machine learning and information retrieval concern this information attribute. For instance, most articles on explainability concern the extent to which information can be interpreted by a human user. So information is the attribute of interest there. From the domain of information retrieval, many articles concern search engine bias or issues of information quality or information balance. And then finally, each article was labeled with respect to the solution or solutions that were being proposed by the authors. So our review, of course, suggests that a comprehensive approach for mitigating algorithmic bias consists of 3 steps. The first one is obviously the detection of bias, so we have to find it first. Here, as Svika also mentioned, there are 2 types of tools which we find described in the literature. So we have auditing and discrimination discovery. Without going into too much detail here, auditing techniques tend to be less formalized, whereas discrimination discovery tools tend to be more formalized. And thus we find that auditing is described by audits can be performed by a range of different stakeholders, including users themselves, by the way. Okay, the second step in the process of mitigating algorithmic bias is fairness management, which Svika talked a great deal about this. It includes the techniques that developers use to mitigate the detected bias and to internally certify that the system is fairness aware. But it has to be noted that just because a system is clearing an internal certification process, it doesn't mean that the users perceive it as such. Therefore, some recent articles conduct studies of fairness perception, and of course in Svika's talk we had a nice presentation of how the different methods for algorithmic bias can aid in the fairness perception of the user. And finally, explainability management is often applied to the system to facilitate transparency and to build the trust between users and the system. So again, without going into too much detail here, the 2 main approaches are black box and white box explanation, with the black box approaches aiming to either explain the global functioning of the model explanation, or more locally a particular outcome with outcome explanation. Okay, so that was probably a lot to take in, so I'll just very quickly give you an example of how 4 articles in our repository are analyzed per our framework here. So from the domain of machine learning, we have the very well read, very well cited 2006 article of Bulukbasi and colleagues, in which discrimination discovery techniques were used to uncover gender bias in word embeddings. Of course, the key problem here is that of data bias, with the embeddings having been trained on Google News articles. Okay, the second example is from the domain of information retrieval, and it's a 2115 JASIS article by Thelwell and Maflahi. This was a user study. They examined how people searched and used literature from Mendeley, and what they found here was evidence of user bias. So users were shown to disproportionately favor articles that are written by authors sharing their own national origin. So of course, national origin is the sensitive attribute in this case. Okay, from the Rexis community, recommender systems, we have the 2017 article by Hanak and colleagues, where they performed an audit on 2 freelance marketplaces TaskRabbit, and Fiverr. And in short, what they found is that women workers and also workers of color were systematically rated lower and with much more negative reviews as compared to other workers. So they described multiple sources of bias. They thought that it was from prejudiced users themselves, third parties or other users, as well as potentially biased training data. So this is an example of auditing. And finally, from the HCI domain, we have the article by Rader and colleagues published in ACM Chi in 2018 concerning the Facebook newsfeed. So they experimented with different techniques for explaining the algorithm's behavior to users. And here the concern is for the interaction of the users with the outputs of the system, and the attribution of interest is information, and of course the solution is of course explainability. After analyzing all of these articles that we collected, I think we have around 260 articles analyzed to date, we aim to study the mappings between research domains, problems, and solutions. So in our Fisheye View, we want readers to be able to zoom in on the particular problem or solution of interest to them. In this, at the same time, of course, seeing the big picture. In this slide, I'm just showing you a quick look at the bias detection techniques, and we have examples from all 4 domains here, and also pointers to specific references that can illustrate each approach. So here, what is interesting to point out is that in all 4 domains that we studied, all of these researchers in all 4 domains are involved in addressing data bias. In addition, we can find examples of both classes of techniques for bias detection. So in other words, we find both examples of discrimination discovery as well as auditing. So as I mentioned previously, the techniques used obviously depend on the stakeholders who are involved. And on that note, so in our analysis, we found 3 types of stakeholders. So first of all, we have observers. So observers are people, of course, who typically have limited access to the process or the system. Researchers, of course, are very frequently observers, those of us who are researching a system to which we don't have access to what's happening inside of it, but also data journalists, as we've seen, and also regulators. Next, we have developers who do have access to what's happening inside of the system or the process. So we use the word developers very broadly here to include anyone who's involved in the development process. So this could be machine learning practitioners, but it could also be the interface designers or those who curate and manage the training data sets. And then finally, the third type of stakeholder that we found is, of course, the users who rely on the system to take a decision or perform some sort of action. Again, here we use the term users very broadly to refer both to people who directly use a system or just people who are affected by the behavior of the system. Okay, so now I am going to switch gears and give you 2 examples from our empirical research, but I'm going to try to relate both of those studies back to our conceptual framework. So first, I'm going to present a specific example of an auditing technique that we use to understand the behaviors in particular, as you see from the title there. To see is to stereotype. We wanted to see how we wanted to understand the behaviors of proprietary image tagging algorithms in terms of their ability to recognize people's gender and the accuracy fairness trade-off. This is a very recent publication of our team, which we presented at CSCW in October, and I was just notified today that the corresponding journal article was published, which is exciting. So to relate this back to our fisheye conceptual framework, this research addresses bias that's observed in the relationship between the input and the output from the tagging algorithms. The solution that we're offering in the paper, of course, is bias detection and specifically auditing. And of course, the stakeholders, the relevant stakeholders here are observers, researcher observers, of course. Image tagging algorithms, or ITAs here for short, are proprietary services. You can see many of the most popular services with which we've been working there on the at the bottom of the slide. So they're very easy to use. They're very economical to use as well. What they do is, you upload an input image, and the output that you get is a set of descriptive tags, which have been inferred as describing the content of your image, of course. And these have become extremely popular, both with third-party developers as well as with academics who want to conduct very large studies of our behaviors on the web or within social media. So the thing is that these tools, being based on deep learning and being proprietary tools as well, they tend to have very little transparency. So a lot of researchers, including ourselves, have turned to performing auditing in order to understand their behaviors. There are two issues that researchers have found which are highly relevant for our research. So the first is that the outputs of ITAs can exhibit gender stereotypes. Somebody was asking about this earlier. So as you can see in the example there, a woman who's dressed in white might be more likely, with a stethoscope around her neck, is typically more likely, as compared to a man dressed in a similar way, to receive a tag of nurse rather than doctor, right? And another very common issue, which I mentioned before, is that these tools can also misgender the people in the input images, as in the second example there, where this woman has been described as a handsome man, actually. So previous auditing procedures or methods have often used images found in the wild, such as the one that you see on the top there from France, which can investigate real use cases. So they're realistic of the types of images that people share on social media. But the drawback is that, of course, we can't control for the image composition. So in a previous work that we published back in 2019, what we did is use standardized passport-style people images with white backgrounds where everyone is pictured with the same gray t-shirt and with a neutral facial expression. And this allowed us to systematically examine the effects of gender and race on the outputs. But, of course, has the drawback that it's not very representative of the types of images that people really share, of course. So in our updated work that we presented at CSCW, we decided to manipulate the backgrounds of those same people images so that we can examine how context may also affect the outputs. So by the way, this is a really nice data set. If you ever need something like this, it's called the Chicago Face Database, and it has 597 such passport-style photos in which the people depicted in these images have declared their gender and their race, and there are a number of, they took their facial measurements, and there are a number of interesting psychometric measures as well. So specifically what we did in our work is to investigate whether the gender inferences made by the image tagging algorithms change when a gender stereotyped context is introduced. So when we put a background in there which is very gender stereotyped. So in order to achieve this, we first chose background images based on context described in the literature, the social psychology literature on gender stereotyping. So for instance, a wedding dress shop or a reception classroom, a kindergarten classroom, might be associated as being more feminine contexts, while a mechanic's garage or a sports bar might be interpreted by people as being more masculine in nature. So it's surprisingly difficult to find images when you need to do an experiment that are royalty-free. And after we managed to find some, of course, we wanted to verify that the backgrounds that we chose indeed signify gender stereotypes. So we asked 100 crowd workers at Amazon Mechanical Turk to rate each one of these images from 0, meaning very feminine, to 9 being highly masculine. And indeed, each image went in the direction that we expected, although some were more extreme than others. After that, we wrote a script to superimpose the standardized people images onto those backgrounds. And the tricky thing here, of course, was to ensure that the ratio of the person to the background remained the same across all images, which, again, was more tricky than you would think due to hairstyles. Okay, so then we sent the resulting composite images through to each image tagging algorithm. And then we finally prepared the descriptive tags, which were output from the ITAs for analysis. We conducted both cross-system and within-system audits. So that's to say we compared the tags received for an image from different ITAs, so looking at the same image, how it's described across different ITAs, as well as comparing the tags received from the same ITA for different images. So looking at how the output changes with the baseline passport style image on each of the backgrounds by the same image tagging algorithm. So I'm just going to briefly go over our findings from 5 services because I can see that time is already getting away from me. So we found that most ITAs, quote unquote, saw more women or men based on the gender-related tags that they output. So yeah, we saw that they saw more men or women in stereotypically gendered contexts as compared to the baseline. That is, they used a different ratio of masculine to feminine tags on a person's image when a context, when a background was added, regardless of whether the gender inference was accurate or not. We also looked at whether or not gender inference and the background recognition are independent events. For some of the image tagging algorithms, gender recognition and background recognition indeed appeared to be independent events, but for others, the ITA was more likely to recognize the background when a gender was inferred, demonstrating that gender and background recognition were interdependents. Overall, we had kind of mixed results for this question because for most of the services that we examined, the recognition accuracy was low, either for recognizing the background or for recognizing the gender of the person. So we continued to analyze in depth only 2 of the services, which were the Clarify and Amazon Recognition, because they were relatively good at recognizing both. And we found that gender inferences were more accurate in a stereotype congruent background. For example, images of men were more likely to receive masculine tags when they appeared in a mechanic's garage, as you can see there, rather than when they appeared in, let's say, a wedding dress shop. We also found that looking at how the descriptions change when we change the background, we also found that descriptions of images depicting some demographic groups of people change more than others when they are placed in a context. So specifically, images of women, images of Black and Asian people actually tend to change more when they're put into context as compared to the images of white men. So also, in line with linguistic expectancy bias, which is, in a nutshell, it's a theory from social psychology that holds that we tend to describe more expected and stereotype congruent people more abstract. So yeah, in line with this theory, descriptions were more abstract when the gender of the person depicted matched the gender stereotype of the context of the background. So for example, men may receive more tags describing their intangible and enduring characteristics when they are depicted in a mechanic's garage as compared to when they are depicted in a wedding dress shop. In conclusion, we found that gender stereotypes affect how often and how well gender is inferred by the image tagging algorithms. And often gender stereotypes seem to kind of, quote unquote, help the inferences on the correct gender. So considering that systems are often optimized for high accuracy, our findings indicate that this can lead to the perpetuation of gender stereotypes. So to go back to our problem space, we can say that we observe that gender stereotypes are alive and well in image tagging algorithms. And we saw evidence that the ones that most closely mimic human stereotyping behaviors are also the ones which are most accurate at gender recognition. So as I mentioned very briefly earlier on, these tools, these image tagging algorithms, are commonly offered as cognitive services that one can easily access through REST APIs. They're extremely easy to set up and economical, as I mentioned, I think. They're increasingly being used by developers and researchers alike. So to go back to our diagram of the problem space, essentially we need to add another layer onto this, because what we have now is a user who's a developer or a researcher who takes the output of this opaque and proprietary system, builds it into another new system or process, which in turn has the potential to affect a whole set of new users. Okay. That was the conclusion of the first example of our empirical work. Here is a second example, which is a bit shorter. So this is work that we presented at the 2019 ACM UMAP conference, and it concerns users' perceptions of the image taggers' behaviors. So in particular, the key research question here is, how do users perceive the output of the taggers in a sensitive context? So we conducted a study with crowd workers on Amazon Mechanical Turk in order to study people's perceptions of tagger and human-produced descriptions of the same images, the Chicago Face Dataset database images. So they were told that today many automated tools are used to generate descriptions of images on the web. However, some tools exhibit biases when processing images of people. Given an image and two descriptions of its content, decide which one is more fair. And then they were asked to imagine that auto tagging is used to facilitate searching profiles of people at a dating site. And they were shown two descriptions, and they were asked which of the above descriptions is more fair, or just enter 0 if you cannot tell. And actually, our main goal was not so much to figure out which descriptions they liked better, but we wanted to understand what characteristics of the descriptions on the people images were important to them in making this decision on the fairness. So in particular, what was important was that we asked them first to tell us which one was more fair, but then please explain your answer regarding your fairness judgment. So this is what they saw. It probably didn't look this pretty on the MTurk platform, but this is the gist of it. So they were presented with one of 8 CFD images, such as this young woman that we see here, as well as 2 descriptions. So they weren't told which description was produced by the algorithm and which one was crafted by a human crowd worker. In our experimental setup, I think, like I mentioned, we used 8 different images, and they were balanced for the gender and the race, self-reported gender and race of the depicted person. I mentioned a while back that this particular data set has all sorts of interesting psychometric measurements for each of the images, one of which is attractiveness. So these are scores that were collected by, so it's social psychologists who put this data set together, actually. So these attractiveness scores were collected by the creators of the data set, and we used images that were rated as being more average, as well as those that had been rated as being highly attractive people. We recruited a gender balanced set of crowd worker participants for each image, and we had a total of 320 participants in the study. Okay, so like I told you before, we first asked them of the two descriptions on the image that they were given, which one do they find is more fair? So overwhelmingly, our participants felt that the human-generated set of tags, descriptive tags, were more fair. However, there were two exceptions, and this was pretty interesting, actually. So the image of the attractive white woman and the attractive white man, for those two, people felt that the tagging algorithm's description was more fair. Why did this happen? We think why it happened is that so we only used one tagger output in this particular study, which was Clarify. And the Clarify tagger tends to be rather interpretive. So it describes some abstract characteristics of people, and it often can use tags like fine or beautiful or attractive. So people apparently find it fair to use those types of tags when someone is attractive. And like I mentioned to you before, what we were really after was for them to explain to us which attributes were important to them in making this fairness judgment. So we just collected free text explanations, and we conducted a thematic analysis in order to see what was in there. And we boiled it down to 6 salient reoccurring themes. Some of them are the usual things that you might expect, like they looked at the accuracy of the tags, or they looked at the balance between objective and subjective tags. But one thing that they mentioned a lot is they wanted to be able to understand. So they wanted to be able to sort of understand the reasons why the tagger said what it said about a given person. So I think this demonstrates the connection between fairness and explainability or interpretability. So only when the users can really understand the description, or when it makes sense to them, did they then see how well it maps back to the person image, and then they can make a judgment as to how fair it was, which makes a lot of sense. Okay, so this is just a quick summary of our findings coming out of these empirical studies. We found that image tagging algorithms treat people images different, and this is systematic. We found evidence that this is systematic across gender and racial groups of the people depicted in the images. So all of the 6 taggers that we used in our experiments used gender-related tags to varying degrees of accuracy, sometimes dependent on the person's race. Interestingly enough, I can say here, if you remember that slide before with the 6 taggers, in early 2020, I can't remember when it was exactly, but early 2020, Google Vision actually announced that it was removing all gender-related tags from the database of its tagger. So, and again, because of the issue with social bias and all of that. So it no longer does gender tagging in its general model. Another finding was that women are described often more than men, and sometimes exclusively, with tags relating to physical attractiveness. Sorry, I actually didn't talk about that here. But it was a finding that came out of that first study. While Black individuals are tagged significantly less often than other racial groups with these sort of attractiveness words. I can point you to the paper for that one if you're interested in seeing the experiment there. And we also saw that when people are asked to explain whether machine output is fair, the extent to which they can understand and interpret the machine is very important. Okay, so this is my last slide. Just going to end with some concluding thoughts, of course. So I'd like to relate our Fisheye View framework and our ongoing research to this emerging science of machine behavior proposed by Rawan and colleagues that you see here. So we've seen, of course, that algorithmic systems and processes, it's well known at this point that they often suffer from social biases and more generally a lack of transparency. And it's often very difficult to understand and anticipate their behaviors. As researchers and practitioners, we face not only significant technical challenges, but we also face the challenges of winning users' trust. So in this presentation, I've tried to provide you with a high-level overview of the field of work surrounding mitigation of algorithmic biases, as well as particular examples of research in which we tried to understand the behavior of black box computer vision applications, in particular image tagging algorithms. So what you see on the screen here is a figure from the 2019 Nature article by Rawan and colleagues in which they advocated for a new interdisciplinary science of machine behavior, which draws both from engineering and computer sciences as well as the social sciences. And as we can see from the author's diagram from this paper, a motivation for developing this new science is that we required quantitative evidence describing machine behavior in order to study the impacts of technology on our lives. So I think that at least in our team, we're trying to align some of our frameworks for understanding bias mitigation to this more general idea of understanding machine behavior. And again, given this European vision for more trustworthy AI, we have to work not only on protecting users from the consequences of algorithmic bias, but also to help them better understand the nature of machine behaviors, its strengths, its limitations, and how, of course, they can best integrate and use these technologies in their own lives. Thank you very much for your attention, and I'm looking forward to the discussion.